Let's do it. Deform. Um, I'm basically going to do what I did in dynamics today. I'm going to go over the syllabus, the structure of the class, um, where to find stuff, and then we'll start with a little bit of mathematical preliminaries for this class. Um, Everything that you'll need in this class is in D2L, so make sure you know how to get into D2L. So once you get into D2L, all your classes will be listed. This is fall. Okay. So here are my classes for this semester. This is deformable body mechanics. Most universities call it mechanics of materials. That's the same class. We call it Deform because that's what the U of Minnesota calls it, but that's kind of unusual. And when you get into D2L for the class, uh, the main thing you need to be aware of is that I'm going to be uh, updating the announcements every class period, sometimes between class periods. You probably want to check that every day, just see if there's anything new on the announcements. And once we start turning in assignments and stuff, there'll be things uh, in grades and under assignments and stuff. But for today, what we care about is content. And this doesn't have everything that it will have as the semester goes on. Mostly today, we're talking about the syllabus, which is under course information. But some other things that'll be useful to know about are assignment problems. This is every class. When I give you your assignment for the class, it's going to come from these. So, maybe at some point I'll say the assignment for today is members in tension and compression, numbers 3, 4, and 5 or something. And so that's how these assignments will be given. You'll turn them in by doing the work on paper and then scanning or taking a picture of it and submitting PDFs of the work. Also, if you want to look ahead, so there's no textbook for this class. Everything is just my notes and videos, but I have some old ones here. So if you want to read ahead, see what's coming up, you can look at this stuff. It's just from a previous semester. So that's all that's up here right now. What we want is the syllabus. So course information, syllabus. Um, and I'm just kind of going to go through this little by little. My name is Gaio Lakin. Call me Gaio. I have a PhD in mechanics, it's called, which is kind of like classical engineering math. And so deformable body mechanics is right in my area of research and stuff during my PhD. The best way to get a hold of me is to use the, let me find it, the instant messenger on D2L. You also can use email. It's just sometimes it's harder for me to keep that organized. Like a bunch of emails will come in and then I'll lose track. And, sometimes I forget to email people back. If you email me and I don't email you back, just send another one and just say, you've already missed one. Don't miss this one or else. And then I'll get back to you in terror. But the if you use this D2L instant messenger, it just is better organized for me so I don't lose track of things, and I'll make an effort to answer those every day. So that's the easiest way to get a hold of me. Here is the class information. My office hours, I'm in here for the 40 minutes between my two classes. So if you have a chance to come early, I can always answer questions before class. And then my other office hours are in the tutoring center. The room number is given there. It's kind of just around the corner from here. And it's Tuesdays from 1 to 3, Wednesdays from 2 to 3. And if that schedule doesn't work for you and you want to talk, I'm always, I can always do Zoom meetings or whatever. The only prerequisite for this class is statics, and we are going to use statics quite a bit. The materials you need, there's no textbook for this class. It's all just based on my lectures. You do need a graphing calculator, and one that does what we need in this class is matrices and vector calculations. If you're in the market for a new calculator, one that does eigenvalues and eigenvectors would be a good idea. But if you already have one you're happy with and it doesn't do that, that's fine. We are going to use eigenvalues and eigenvectors in this class, but you can compute those on your phone now. And when we use them, like on tests, when we use them, I'll always give you workarounds so that you don't have to do those calculations on the exam. But we are going to do a lot of eigenvalues and eigenvectors. These recommended reference books, I actually don't recommend these as when the semester is going on. I would say think of your job as just understanding what I say, understanding the assignments I give. It should all be self-contained. These are mostly on here so that if there's any issue with transfer when you go to a different university, the professors know what stuff I'm covering in this class, so they know what's the appropriate transfer. For people, we have things where people transfer to University of Delaware or something, and then they don't know anything about our program, so then they have to look through the classes and figure out how things transfer. So that's why I list this book by Gear and Goodnow. It is a good reference book, but really I would only use these if you want a reference book after this semester ends. While this semester is going on, I would just try, just understand what I'm talking about. The Gear and Goodnow book is a well-known, like, full textbook, so it's expensive. The Shams outline is cheap, $25 or something, paperback, and it has a ton of problems with solutions. It's really nice if you're getting ready for a standardized test or something, say. The topics we're going to cover, we're going to do a little background in matrix math because everything in this class is pretty much going to be done using matrices. And we'll introduce the stress tensor. And so stress and strain are really what this class is about. It's sort of an introduction to the ideas of stress and strain, ways to calculate and predict damage to materials and fracture. Then I don't think I look at this. There's 31 topics. You can look at these if you're interested. I'm not going to read through these all, I don't think. But the basic idea is that we're going to expand on what we've done with internal loads. And I'll go back over internal loads if anybody took a statics class that didn't cover that. And then we're going to use those internal loads to take the next step into calculating stresses and strains at points. And those stresses and strains are then what are useful for predicting fracture and things like that. The grading will most likely be pretty straight, 90, 80, 70, 60. If, there's sometimes cases where I have to curve the class a little bit. So I might do that, but it's usually quite close to 90, 80, 70, 60. And the grade will be broken down as follows. And so I'm going to go through each of these categories and just explain what I'm talking about. So we're sort of going up from the smallest part of the grade up to the biggest part of the grade, which is exams. The first one is professionalism, consistency, and appropriateness. And this is just me trying to nudge you towards the kind of behavior that'll translate well when you transfer to the university that you go to, and that'll work well for you when you start working as a professional, as an engineer. And so it's basically like a kind of a just mashup of all these things. The first one it mentions is attendance, and I just want to be very clear that right now there's a lot of things going on in the Twin Cities that are not safe for lots of people, and I do not expect you to make yourself feel unsafe to come to class. So this attendance thing, I'm not worried about that for now. We'll see what happens as the semester goes on, but all I really want you to do for now is keep me updated on what your attendance sort of situation is. If you're gonna be missing a lot of physical class, just keep me updated on what your status is, that kind of stuff. Okay, I just want to stay in the loop, but I'm not going to be marking anybody off at all for missing class right now. Punctuality is also part of it. Just get in the habit of being on time when you come to class, when you come to tests. Consistently turn work in on time. I'm always flexible with due dates. I know that people have other things going on, but if you're turning in your homework in big chunks regularly, or you're missing the due dates regularly, that's the kind of stuff that I'm grading on in this first chunk of things. Coming to tests, you should have a writing utensil, you should have a calculator with batteries. If it's not too hard to just throw some batteries in your bag and have them there if your calculator runs out. An appropriate level of class participation, largely to me, just means not being distracting. There's a point where asking questions crosses over to sort of derailing the flow of the class. And I'd be happy to talk to anybody about that who wants to talk about it. But other than that, I don't have much to say about it. If you feel like you're not sure where that line is, I'd be happy to talk to you about it outside of class. A reasonable use of exam rescheduling, again, I'm flexible on rescheduling exams, but there are always students who want to reschedule every exam, and that I don't think that's appropriate. If you're using the OSD office, you should be providing me the OSD forms. They should be filled out. All of this is just part of being, getting in the habit of working with other people, part of a professional degree. The work you submit needs to be legible. I need to be able to follow the arguments that you make in your assignments. When you lobbying for grades, there's a point where that becomes excessive. I'm always happy to talk about I think you missed what I did here. I'm always happy to talk about it. But when it's the same people every single exam, that's too much. And then following assignment instructions. If I say I want assignments turned in as a single PDF and you're turning in assignments as 12 separate JPEGs, that's not following instructions. Anybody have any questions about anything in that category? Okay. Um, and then 5% of the grade is based on lecture quizzes. Um, every couple of weeks, and I'll tell you beforehand when these quizzes are coming up. We'll end the Wednesday class with a lecture quiz that's just short answer questions about what I say in class. So this is just designed to make you periodically, regularly go back through your notes, um, read your notes, skim your notes, just be very familiar with what I'm saying in the class. I'll try to make these quizzes focus on what I consider to be the bigger ideas and not be, just really picky minutia or whatever. But I'm just trying to get you to read your notes, reread your notes, know what I said, be able to repeat, paraphrase what I said. You can't do the problem. If I didn't think it was important to say these things, I wouldn't say them. So I want you to try to remember what I say. Then 10% of the grade is daily assignments. And I give you solutions to the daily assignments. And the ones that I don't give solutions to, I'd be happy to, if you can't figure out how to do the assignments, bring them up in class and I'd be happy to do them for the class. So getting the solutions to these problems isn't the issue. You're just trying to do these assignments to solidify these skills. Um, and I'm not grading these when you turn them in. I'm not like looking at them and because you have the solutions, you have access to solutions. I'm just checking off whether you turn them in, but I'm just trying to keep you on schedule by assigning these. Also, um, I think like a ballpark idea of how much time you should be spending on this class, like putting in the lectures, the studying, the reading, the assignments, everything should be about 10 hours a week. That's kind of the ballpark of what a 3-credit class should expect. So if you finish the things that are assigned and you still have more time left to work on this class in your 10 hours, you should be going back to these daily assignments a week later, 2 weeks later, whatever, and trying to do these and seeing if you can do them without looking at the solutions, okay? What we're doing is we're trying to solidify these skills, and that takes some repetition, okay? Um, now, the daily assignments are not a big chunk of the grade. It's only 10%. But if you consider the fact that the exams are based entirely on these daily assigned problems, this whole class is really about gaining an understanding of these problems that I assign. Okay, so yeah, 10%, except if you don't do these assignments, you don't lose that 10%. You lose that and most of the exam things too, because you're not getting yourself ready to take the exams, Um, and these daily assignments should be turned in as a single PDF file. And I'll tell you more about that later. Then 10% of the grade is weekly assignments. So these are ones I'll give you an assignment maybe every third week or something. And these are ones that I'll grade carefully. I won't give you the solutions for. So this is a chance to get a little more feedback on the work that you're doing. But they're no more difficult really than the daily problems. It's just I'm making sure that you're going through these the right way, using the right notation, your arguments make sense, that kind of stuff. Any questions about the assignments, the daily or weekly assignments? Um, and then the biggest chunk of the grade, 70% of the grade is exams. There are 4 of these, so they're each worth 17.5%. Each exam is cumulative to that point up in the class, which means every exam is going to, you have to be ready for the first stuff we do in this class for each one of these exams. It's not just the material that we've covered since the last exam. It goes all the way back to the beginning. The exams are calculations. It's not short answer like the quizzes. So getting ready for the exams is entirely about going back over the daily and weekly problems and making sure you understand those thought processes, know how to do that stuff. Okay. There is one kind of makeup policy. It's not makeup exactly, but if you score better on the final than you do on any of the first 3 exams, the final score can replace one of those first 3 exams. So if one of these goes badly, but then the final goes well, the final will count as, say you get a 90 on the final, then it will count as a 90 on the final, and it will also replace your lower score with that 90. Okay, so it just gives you a little wiggle room if one of your tests goes badly. Anybody have any questions about the exams? The dates are given here. If any of those dates are going to be a problem for you, let me know as soon as you can. Like I said, I'm happy to be flexible with this stuff, but kind of up to a point, and I think, but I know that everybody has other obligations, and I try to be flexible when I can.
When will the final exam take?
I have not had that emailed to me yet. When will we know?
Yeah.
I think it's usually pretty soon. Usually I get that before the semester starts, so I'll try to get you that information soon.
Okay.
Any other questions right now? Cheating, well, don't copy other students and don't use AI, basically. And then if you're interested, there's a lot of information on the website, that I've gotten from the Normandale website. Learning outcomes, some sort of overall statements, Title IX stuff. So there's some more information you might want to glance over related to the syllabus. Okay, so that's it. Anybody have any questions about the structure of the class? Well, the first assignment that I'm going to give you is going to be a vector review. You're going to read this vector review, and then there'll be some problems to do. Let me show you what that looks like. I mentioned this in dynamics. I know there's a lot of overlap between dynamics and Deform. So anybody who's in both of those 2 classes, you only have to do this assignment once. Okay. Yeah. Yeah. Oh no, you can just turn it in one class. I'll know who's doing what class. Okay, so here's what the vector review looks like. I got it under course information. So it's just some stuff to read. It talks about the notation that we're going to use. Some calculations that are going to be important for us. The people who took statics from me, you've done this assignment before, but that's okay. Like I said, there's repetition is helpful. It helps you remember stuff. So you don't have to do it for dynamics and Deform, but even if you've done it for statics, just do it again. So there is the reading part of it, and then under assignment problems, uh, here are the problems associated with it. Okay, so I'm not going to right now go into this vector review. That's something I'm going to have you read and work through. But of course, if you have any questions or problems about the assignment or the reading on Wednesday, I'd be happy to talk about that at the start of class. So bring your questions, and I'd be happy to go over any of the problems. But today, what I want to do is start doing some of the other mathematical preliminaries for this class, which is mainly just matrix math.
Can you just review that?
The matrix stuff. Not everybody has done this matrix stuff before, so for some people it'll be some review. Even for the people who've seen it before, I think it'll be helpful just to see what's the important stuff for this class, you know. So okay, mathematical preliminaries. Matrix math. And it's going to be really important that you get used to doing this matrix math on your calculators. These calculations are going to come up in all the exams and stuff. So I'll try to sort of summarize what you need to know about your calculators as we go. I do have one question. How many people in here have graphing calculators that are not Texas Instruments? HP? HP?
Yeah, this is 9750 GA.
By what company?
Casio.
Okay. So some of those, I mean, if you have trouble figuring out how to use the matrix stuff, I'd be happy to talk to you about it. I'll bet we can figure it out together. But I'm familiar with TI calculators. Okay, so when I talk about a matrix variable is always going to, I'll give it like a little under squiggle. In printed text, often instead it'll just be boldface is what they'll do to indicate that something is a matrix. And so I'm going to just write down this arbitrary matrix, and then we'll talk about some of the characteristics of it. So let's say this matrix is 2, 1, and then the next row is -2, 4, and then the next row is 0, -6. And this is called a row, and this is called a column. And overall, for the size of a matrix, you give the number of rows and then the number of columns. So this is called, the size of this is called 3 by 2. Okay, because we have 3 rows and 2 columns. So the size is given as the number of rows by the number of columns. If you're talking about specific elements from a matrix, the subscripts of the element are the row followed by the column. So if we're going to go through these 6 elements, the element 1, 1 would have a value of 2. The element, we're still in the first row, and now we're in the second column, so this would be 1, 2 is the value 1. A2, 1 has the value -2. A2, 2 has the value +4. A3, 1 has the value 0. And A3, 2 has the value -6. Yeah, that's just a pretty common notation. That's not always used, but often we will use. So let me write this. So most often, matrix variables will be capitalized. And the element variables or the elements will be lowercase. To enter a matrix into a TI calculator, I'm going to do this for the different TI calculators. Now, so I said, if you're having trouble figuring anything out on your calculator, come talk to me and we can figure it out. That's probably true, but AI can probably tell you exactly how to do it. So that option wasn't available a year ago or 2 years ago, but it probably is now. So, okay, if you're using a TI-84 or 80, well, let me do it in order. If you're using an 83 or an 84, or I think an 86, to enter a matrix, you have to go to the matrix environment. I think that's like a second function usually, and then the math button. And then you have to go to edit, and it'll just let you enter value by value this matrix. If you're using an 84, so the 84 gives you a couple of options, or if you're using a TI-89, you can enter a matrix this way: a square bracket to start and end the matrix, and then square brackets for each row. So you do the rows individually, and you can separate them with columns or spaces, I think. So this would be, so start the matrix. Now start the first row. And I'm going to use this matrix up here above. So the first row is 2, 1. So go 2, column 1, 2, comma 1. End the first row. Now the second row is -2, comma 4. And then the third row is 0, comma -6. And now we're done with all the rows, so end the matrix. And then the TI-89 also gives you a second way to do this. So the 89, you can also separate the rows using a semicolon. So you could also do a square bracket 2 comma 1, then semicolon, -2 comma 4, semicolon, 0 comma -6, and then end the matrix. So that saves a few keystrokes if you have an 89. And then for an inspire, this is the last one. There is sort of a button over on the right side that looks something like this.
It's the diff of the multiplication online.
On your Inspire?
My Inspire.
Okay. Most of them have a button like this, I think, but I remember yours was maybe an earlier version or something. Yeah. So but anyways, you have to go into like a matrix environment, and then you have to enter the size of the matrix, and then it'll just let you enter using the keypad. In this class, we are basically only going to use 4 matrix sizes. So I want to talk about the different ones. The first one is a 3x1 matrix. And this will denote vectors in 3D. So like an example would be a force vector of like 10,000 newtons in the x direction, negative 15,000 newtons in the y direction, positive 5,000 newtons in the z direction. And then we'll see that we'll also use this for tractions. At a point inside a material. And tractions will have units of, well, let me write that as a t vector, and I'm just making up values, but let's say we have 10 to the 5th, let's see, and then 0 for y, and then negative 5 times 10 to the 5th for z. And the units for tractions are going to be pascals, which is a Newton per meter squared. The second size that's going to be important to us is 6x1. And we'll use this for what's called the Voigt form of stress and strain. And so the Voigt form of the stress would be the only thing that's really important to notice right now is stresses are generally going to be very big values. Strains are generally going to be very small values. So a Voigt stress might be something like 2 times 10 to the 6, 0, negative 8 times 10 to the 6. I'm making up numbers again. 0, 0, and then 1 times 10 to the 7. And this would have units of pascals. So this is the Voigt stress. And the Voigt strain, on the other hand, all the values are going to be really small. So this could be like 1.5 times 10 to the minus 5, 0, 0, negative 6 times 10 to the minus 6, 0, 0. The stresses have units of pascals. The strains are going to be unitless. They're just numbers. So this is an example of a Voigt strain. Then the third size that we're going to use is 3 by 3. And this will be stress tensors. And rotation matrices. So an example of a stress tensor, I'm going to use that Greek letter sigma again that I used for the Voigt stress, but I'm not going to put the V there. That V is for Voigt. And this would be an example of a stress tensor would be like 6 times 10 to the 6th, 0, negative 8 times 10 to the 7. Then the next row, 0, 5 times 10 to the 7, negative 2 times 10 to the 7. Then the last row is negative 8 times 10 to the 7, negative 2 times 10 to the 7, and negative 5 times 10 to the 7. And this has units of pascals. And this is a stress tensor. And one thing that we'll, talk about more, but worth noticing for a first time here, is that if you isolate the main diagonal of this stress tensor, notice that there's symmetry across that main diagonal. This is equal to this, and this is equal to this. And I guess there's one more here. This is equal to this. Okay, so the stress tensor is always a symmetric matrix, it's called, and that has certain mathematical properties that are going to be useful for us. And then the second type is a rotation matrix. And I'm going to make one of these up using values that, so let's see. Let's say 0.7071. Let's use a different one. So let's say 0.866, 0.5, 0, negative 0.5, positive 0.866, 0, and then 0, 0, 1. So this is an example of a rotation matrix. It's unitless, it's just numbers. And it is an example of an orthogonal matrix that has certain properties. The word orthogonal would make you think that some things are perpendicular, and you can see that if you think of each one of these columns as a vector, those three columns are all perpendicular to each other. So those are the two 3x3 matrices we're going to use. And then the last size that's going to be important for us is 6x6. And this will be the compliance matrix. That I'll denote as capital C. And this is also the size of what's called the stiffness matrix. And the stiffness matrix will denote with a capital E. And I'm just going to give one example because this is a lot of values, but excuse me. One thing about these is that these are inverses of each other. So the compliance matrix is the stiffness matrix inverse, and vice versa. So if you can calculate one, your calculator will easily give you the other one. You just have to use the inverse button. And the compliance matrix looks like this. So for the first row, we have 1 over a value E, negative Greek letter nu over E, negative nu over E, and then 3 zeros. The next row, we have negative nu over E, 1 over E, negative nu over E, 0, 0, 0. The next one, we have negative nu over E, negative nu over E, 1 over E, 0, 0, 0. So you can see that 1 over E just keeps creeping along there. We're half done with the matrix now. So the next row is 3 zeros. And then in the fourth spot, we have 2 times the quantity, 1 plus nu over E, 0, 0. And now that funny looking term just creeps along as we go. Yes?
What's the Greek letter you're using?
That's nu. It sort of looks like a scripty V, lowercase v.
What does it represent?
So the E and the nu, each one of them represent a material measurement that you can take. So if you have a lump of some unknown metal, you can take some measurements to get those values. And then based on those values you measure, you can fill out this matrix. Okay. Other than that, I know right now none of this will make a ton of sense. I'm just getting your eyeballs on it for the first time, but we'll talk about it a lot more later. And so now this value just keeps creeping along. So now we'll go 0, 0, 0, 0. And the fifth value is 2 times the quantity 1 plus nu over E, and then 0. And then 1, 2, 3, 4, 5, and the last value is 2 times 1 plus nu over E. And so there it is. That's our 1 6x6 matrix that we're going to use.
And it's always gonna look like that.
Yeah, I mean those numerical expressions, those algebraic expressions, are always just going to be numbers that we've gotten from some other measurement or something. But yes, that is what it always is going to look like. And okay, so what is this thing? The Voigt strain that we talked about before, which is a measure of a body's deformation at a point, is equal to the compliance matrix times the Voigt stress, which is a measure of loading of the material. And because of the inverse relationship thing, the Voigt stress is equal to the stiffness matrix times the Voigt, strain. Stiffness matrix times the Voigt strain. In other words, okay, you can think of this messy looking 6x6 matrix as like a three-dimensional version of the spring constant of a material. Okay. So you can think of the compliance and the stiffness as things that relate loading to deformation. And so you can think of it as kind of like the spring constant K from physics. Okay, well, the compliance, a values in the compliance matrix are bigger if the thing is easy to, stretch or whatever. And stiffness values are bigger if the thing is hard to stretch and compress, So since we're talking about engineering materials, think of a giant chunk of steel. Would you be more likely to be impressed by how easy it is to stretch or how stiff it is,
Right.
Well, like it always depends on the loads you're applying, but like to our everyday experience, like a hunk of steel, we can't bend it in any meaningful way, So you'd expect the stiffness values of engineering materials to be high and the compliance values to be low. And that's how it's going to work out. If you have a stiffness matrix, these elements are going to be stuff times 10 to the, say, 11th power. And compliance values are going to be stuff times 10 to the minus 10th and things like that.
Is this, we assume that the material is uniform, maybe like it's made out?
Yeah, we're going to have to have a lot of discussions about what requirements we're going to give for materials.
Like a piece of wood has several layers, but have differing layers?
Yes, you are exactly right. And we're going to have to talk about all that stuff. But the calculations that we're going to do are all going to be stuff that doesn't have preferred directions. So for the most part. So like, for example, steel, unless you've created the structure in a very, very careful way, steel has no preference for how strong it is this way or whatever. Whereas exactly like you said, bone or wood or something like that, stuff coming out of a 3D printer, that's going to have sort of different properties depending on which direction you load it. Okay, so there's only 4 matrix sizes that we're going to deal with, and those are the 4. Now I want to talk about some important matrix definitions. The first one is the transpose. And the definition of the transpose is this. If you have a matrix B that's equal to the transpose of a matrix A, and the transpose is given by that, it looks like it's to the power of capital T. That's the symbol for transpose operation. What that means is that B I J, the ijth element of the B matrix, is the jith element of the A matrix. Okay, so what the transpose does is switch the rows with the columns. So an example of this is if you have a matrix A that is, the first row is 1, 2, the second row is 3, 4, the third row is 5, 6. Then A transpose, you're just switching the rows with the columns. So this would be a first column of 1, 2, a second column of 3, 4, and a third column of 5, 6. And you can think about it in terms of the definition that I gave you here above. Like, think about so this 3 in the matrix A, that is the element, it's the second row, first column. So that's the element 2, 1. And so the 3 over here in the transpose matrix is the element 1, 2. It's in the first row and the second column. You're switching what's the row and what's the column. One thing to notice about this transpose operation is the transpose of an M by N matrix is an N by M matrix. And TI calculators, so let's say this is the first thing to notice. The second thing to notice is TI calculators have a built-in transpose function. Um, the second definition that we need is the inverse. And the definition of an inverse is that it's really the same definition as a multiplicative inverse. Like the number 2 and the number 1/2 are multiplicative inverses of each other. That means if you multiply them together, you get the identity, you get 1, right? That's what an inverse means with numbers. With a matrix, if you multiply a matrix times its inverse, and it doesn't matter the order, you get the identity matrix. So the identity matrix looks like 1s on the main diagonal, and then 0s everywhere else. And the order doesn't matter for this. So in general, the order of multiplying matrices does matter, but it doesn't matter for this inverse definition. So the inverse times the matrix is also equal to the identity matrix. The inverse and the transpose are not the same thing. There's no reason to think that they would be. So generally, they're not the same. But for orthogonal matrices, like the rotation matrix that we saw, I'm going to say that a rotation matrix is this matrix Q, then Q transpose is equal to Q inverse. On TI calculators, so notice in TI calculators, you can calculate the inverse by raising a matrix. Oh, my computer does this sometimes. Just a sec. So you can calculate the inverse by raising the matrix to the -1 power. So like when I was talking about the compliance and stiffness matrices, if you calculated this compliance matrix and you wanted to know what the stiffness matrix was, you know it's the inverse. So you could fill out this matrix for the compliance and then raise it to the power of -1, and it'll give you the 6x6 matrix of the inverse. The third definition is a square matrix. And this has a very intuitive meaning. It has the same number of rows and columns. For square matrices, we're going to define diagonal and off-diagonal elements. So diagonal elements have indices where I is equal to j. So in a square matrix with 3 rows and 3 columns, the diagonals are the 1, 1 element, the 2, 2 element, and the 3, 3 element. And the off-diagonal elements have indices where I is not equal to j. So for example, if we have the square matrix 2, 6, -1, 0, then these are the diagonal elements. And this are the off-diagonal elements. And then the last definition we'll do today is a symmetric matrix. And a symmetric matrix always has to be a square matrix. So it's a square matrix where Aij is always equal to Aj. Or in other words, the matrix A is equal to its transpose. Those mean the same thing.
Can you please add an example for it?
Yeah. So which of these is symmetric? So let's say we got 5, -5, 1, and then 0, 2, 3, 0, 0, 2. So that's the first one. And then the second one is -6, 0, 0, 5, 2, 5, -1, 2, -1. Okay, so one of these is symmetric and one isn't. So you can see that. So visually, like, let me just do it sort of visually first. So think of canceling out the diagonal. That can be anything. And now think of the elements that are reflected about this diagonal. For it to be symmetric, this 1, 2 element has to match the 2, 1 element. The 1, 3 element has to match the 3, 1 element. And the 2, 3 has to match the 3, 2. Okay, so with this one, you can see right away that that doesn't hold. The 2, 1 element is 0. The 1, 2 element is 0. The 2, 1 element is 3. So that doesn't work. This one, on the other hand, the 1, 2 element is 5. The 2, 1 is 5. Okay. The 1, 3 is 2. The 3, 1 is 2. And then the 2, 1 is -1. The 1, 2, the 2, 3 is -1. The 3, 2 is -1. And so this is the one that's a symmetric matrix, and this one is not. There's one thing that's useful about symmetric matrices. We haven't talked about eigenvalues and eigenvectors yet, but they'll come up later. And the key thing here is symmetric matrices always have real eigenvalues. So that'll come up later. In general, eigenvalues are complex numbers, but if you have a symmetric matrix, the eigenvalues are real numbers. And that's going to have significance to us in the way that we use, because we'll be doing eigenvalues of stress tensors, which are symmetric matrices. And so those eigenvalues for us are always going to be real. Any questions? That's just a lot of talking and listening, but next class, we're going to talk about matrix multiplication, and then we'll start applying this stuff to physical things. Okay, and look on D2L later today for the assignment. It'll be reading that vector thing and doing some vector problems. And if any of the problems are tricky for you, or you want me to explain them, bring your questions on Wednesday, and I'll spend as much time as you want going over that stuff. Assignments are always going to be due by midnight of the next class. So the assignment I give you today will be due by midnight on Wednesday night. And then I always give you a 1-day grace period anyway. So it says it's due Wednesday at midnight. The Dropbox will really be open until Thursday at midnight. I would recommend, if you can find the time, do the assignment, or at least a significant amount of it, before class on Wednesday, because then when we talk about the problems, it'll be helpful to you instead of something you haven't seen yet, you know? Okay, goodbye.
You said the matrix is the same as the square matrix?